Welcome to this video explaining exactly what ordinary least squares linear regression is and why it's such a powerful tool. And as I say to a lot of my undergraduate students, if you are struggling to grasp what OLS is all about, you're probably overcomplicating it. It is a relatively simple concept, and so today I'm going to break it down very slowly for beginners and perhaps for those who have had a look at it and feel a little bit lost. In order to understand what a regression is and why it's so useful to us, we first have to have a really solid understanding of the equation for a straight line. And as you're going to see later on in this video, a linear regression is just a glorified straight line with some bells and whistles attached. So here I have given the equation for a straight line, and I've given it as y equals a plus bx. You may have seen other variants of this equation. Common example is y equals mx plus c, but it doesn't matter. They all mean exactly the same thing. The reason I have decided to present this as y equals a plus bx will become clear once we've got a solid grasp of the equation and understand why a straight line equation is so useful to us. We're going to convert that understanding into the context of a linear regression, and it will make sense why I've used this form here. Now, what are the different elements of this equation? So you can see in the red we have y and x, and these are what we call variables. And a variable is just something that we measure that can change from observation to observation. So for example, imagine I'm measuring the heights of current Premier League footballers. Their heights are considered a variable because I can measure them, and this measurement can change from observation to observation, i.e. from player to player. In green, we have A and B, and these are what we call parameters. And a parameter is something that we can measure, but it doesn't change from observation to observation. There's only one value to a parameter. Imagine that I wanted to calculate the average height of current Premier League footballers. There is only one number for the average height. It is one thing. There's only one average height of that population. So this is a parameter as opposed to a variable because it's something we measure that doesn't change value. Now, the parameter A here is what we call the y-axis intercept. It tells us the value of y when x equals 0. So you can imagine in this term here, if x was equal to 0, b times 0 is 0, this term disappears, and y is equal to a. And it will become clearer as to why we call it the y-axis intercept when we come to plotting this straight line on a graph shortly. B here is what we call a slope coefficient, and it gives us our gradient. Importantly, b tells us how much y changes when x goes up by 1. And again, this will become clearer to visualize when I show you how this works with an actual graph. Now, in order to demonstrate how this straight line equation works and why it's so useful for us, it's helpful to assign some numbers to the parameters a and b. And I've gone for a equals 1 and b equals 2. So if I was to plug these into our equation for a straight line, we end up with y equals 1 plus 2x. And importantly, what this equation allows us to do is calculate y for different values of x. So for example, when x is equal to 0, this equation becomes y equals 1 plus 2 times 0, which is 1. When x equals 1, this equation becomes y equals 1 plus 2 times 1, which is 3. And we could plug 2 in and get 5, 3 in and get 7, and so on and so forth. And at the end of the day, what we end up with is a lot of x values and their corresponding y values. And what we can do is we can take an xy graph and we can plot these coordinates on that graph. Okay, so you can see when x is 0, y is 1. So when x is 0, y is 1. So we're going to have a point just there. When x is 1, y is 3. So we're going to have a point around there. And so on and so forth. I can go on plotting all of these values. As you can see, all of these points are on a straight line. So essentially, what our equation here does is it allows us to plug in values of x and get a value of y that corresponds to that value of x, and all of those points sit somewhere on this line. But the question is, why is this so powerful, and what useful information can we gather from this equation? Well, this equation allows us to do three very important things. Firstly, and as I've already mentioned, we can see the value of y when x equals 0. So the value of y when x equals 0. And you might ask yourself, well, why do we care about this? Why do we care what the y-axis intercept is? Well, let's imagine you work for Nike and you're selling trainers and you want to know how much advertising impacts your sales. So you could have sales on your y-axis and advertising on your x-axis. And you could tell that if you have 0 units of advertising, or you don't advertise, you will have 1 unit of sales. The second really important thing that this equation allows us to do is indicate how much y will change when x goes up by 1 unit. And this is given by our slope coefficient, so the number in front of the x, which is 2 here. And you can see it on the graph as well. When x goes up by 1 unit, y goes up by 2 units. And again, x goes up by 1 unit, y goes up by 2 units. And that's indicated by this thing here. And this would be practical for our hypothetical Nike employee, because they can see that if they want to increase sales, for every unit of advertising they do, sales will go up by 2 units. The third important thing that our equation here allows us to do is predict y for all values of x. And we can do this with the equation or on the graph. Say we want to know what y is when x is 2.5, we can plug it into our equation here and get y is equal to 1 plus 2 times 2.5, which is 6. Alternatively, we can go to our graph here, find out where x is 2.5, go up and see that corresponds to a value of 6. So now our Nike employee knows that if they want to sell 6 units of shoes, of trainers, they'll have to do 2.5 units of advertising. So what is a linear regression? Okay, clearly the equation for a straight line gives us some really useful information. It gives us our y-axis intercept and the slope parameter, and we can use these to calculate y for any value of x. The question then begs, where does a regression come into this? And the clue's in the name really. The term regression sort of implies to move backwards, and that's exactly what a regression does. So before, on the last slide, we had our straight line equation, and we used this to generate data, the x and the y values. With a regression, it's the other way around. We start off with our data and work backwards to create an equation for a straight line. So sticking with our shoe sales example, let's say we've collected data from the last 5 months on how many units of advertising we've done and how many sales we've made. And the first column just indicates the month in which we've collected the data, i.e. t equals 1 is the first month and t equals 2 is the second, and so on and so forth. The second column, our x variable, it measures how many units of advertising we've done in each of those months. And then finally, the third column is our y variable, and this measures how many units of sales we've made in each month. And using this data, we can plot our x-y coordinates just like before. However, you might be able to spot the problem here. We want an equation for a straight line. As you can see, our data points aren't in a straight line. But this is what a linear regression is. All a linear regression does is plot a line of best fit through our data, and it gives us an equation for a straight line. The way in which we find the line of best fit is through a procedure we call minimising the sum of squared residuals, but I'll cover that in another video. But essentially, once we have this straight line, we have our y-axis intercept, we have our slope coefficient, and with those things, with that straight line equation, we can make those useful inferences. Now, given that on our regression the y-axis intercept was 1 and our slope coefficient was 2, we can write out our regression equation like this equation at the top here. But generally, before we know what our parameter estimates are, we write out our equation in its general form, which is this here. And we label our y-axis intercept beta 0 and our slope coefficient beta 1. And if we compare our regression equation in its general form here to the equation for a straight line here, you might notice they look very similar, and so they should. They both contain our y variables and our x variables. They both contain our intercept terms. Here it's beta 0, here it's a. They both contain our slope coefficients. Here it's beta 1, here it's beta. There's only really 2 differences between these equations. I mean, there's 2 additional things in the regression equation that aren't in the equation for our straight line. these additions are, the regression equation has t, little time subscripts here, and it also has this thing at the end, which is an error term. Okay, the error term simply captures the vertical distance between our data points and the line. So, for example, here the distance between our regression line and the data point is +1. So the error term is 1. Here the error term is -1, -1, 1, 0, and 0. So we call it an error term because it is the difference between the value of y our regression line predicts for that specific value of x and the actual value we observe. So it's the vertical distance between the data point and the regression line. The t subscripts just represent the individual time periods in which we observe yx and the error term. So for example, if you wanted to work out the value of y at the third observation, you would say it's equal to β0 plus β1 times x at the third observation plus the error term at the third observation. So this serves as a sort of roadmap to get to a specific observation at a time period of your choosing. Now, so far, we have only looked at singular linear regression, meaning that we've only included one independent variable, in this case it's x. And because we've only had our x and y variables in the model, we're able to plot this on a simple scatter plot with an x and y axis. And from this we ran our regression and estimated our parameters, our intercept parameter and our slope parameter. And it's important that you remember we interpret β0 as the y-axis intercept, so it's the value of y when x is equal to 0. And we interpret our slope coefficient β1 by saying that when x goes up by 1 unit, y changes by β1 units. It is, however, possible to have two independent variables. So with this new regression on the right-hand side, we have both x and z as independent variables. And if we were to plot this on a graph, it would have three axes and look something like this. And in this instance, instead of a line of best fit, we have a plane of best fit. But importantly, and then the key takeaway from this part here is how we interpret our intercept term and slope coefficients doesn't change. We would say that if x goes up by 1 unit, y changes by β1 units, and if z goes up by 1 unit, y changes by β2 units, and if x and z are equal to 0, y is equal to the intercept term. Okay, so just because I've added another independent variable, which has created another axis on our graph, the way in which we interpret our coefficients does not change. And in fact, we can have a regression equation with 3 or even more independent variables. When you've got 3 or more independent variables, these graphs are impossible to visualize because we can only see in 3 dimensions and there'd be more than 3 axes. But the point I really want to get across to you is our interpretation of the coefficients doesn't change no matter how many independent variables we have. Your intercept coefficient, it will always tell you the value of y when your independent variables are set to 0, and your slope coefficients always say how much y changes when the independent variable goes up by 1 unit. And in a nutshell, this is all OLS linear regression is. I mean, there are some caveats, like, before we make any inferences from our estimates, we have to do things like testing for significance and making sure the model adheres to a set of assumptions we call the Gas-Markov assumptions. And if we don't adhere to those assumptions, we can't rely on our estimations. But I'll cover these in future videos. So as I say, that is OLS in a nutshell. If you have any questions or want to request a topic for me to cover in another video, please leave me a comment. But other than that, thank you very much for watching.